I've given names for some of these rules like max rule, sum rule. This is another one. It's called the product rule of big O. So some people will call it this. And it goes like this. And I warn you in advance, it's going to have a little bit more going on with the statement, but I assure you, the way that the statement gets set up makes it really easy to prove. At least I think it is. Or at least I hope to convince you that the way we ration through the reasoning is actually really nice. So at first, it's going to look like there's a lot of bookkeeping. Definitely not as much as most cases we've had it. So we're going to have there's going to be 4 complexity functions, 4 arbitrary ones. Let there be 4 complexity functions. So again, you could think of these like an n and an n squared, an n cubed, a log base 2 of n, 2n, whatever you'd like. Let there be 4 complexity functions. Functions, we have f1, we have f2, and we have g1, and we have g2. Sorry, I was not the right put the 2 inside of there. So we have f1, f2, g1, and g2. So these are 4 functions. So if I know if f1 is big O of g1, and f2 is big O of g2, you might guess quite quickly where this is going if I call it the product rule. Then it has to be when I take the product of f1 and f2, there has to be big O of g1 times g2. Then f1 times f2 is big O of g1 times g2. So like I said, it's a lot of busy work kind of getting this all set up. But once you have this in place, it's actually, believe it or not, the setup for this proof is going to remind you a little bit of what we did in some previous examples. So here we go. And here's the intuition behind this. Or at least this is one intuition you can use. We know f1 is big O of g1. We know f2 is big O of g2. We have these 2 things that we can use. So it means we're going to get constants for each one of them. We're going to use what we called existential instantiation. So this statement involves the existence of 2 constants. That's why our definition works. So that means we can actually give those names, and we can use those variables, which are constants, right? We call them constants just for the sake of clarity. So I have names for those. And then I'm going to just find a way to mesh them together so that I can form a statement that gives me this. That's going to be what we're going to try doing. But you might ask, Dan, why would we care about this product rule? Well, suppose, for example, I'm going to give you a setting, for example, that comes more from programming. So, for example, suppose that G1 and G2 are total numbers of operations that happen. One for, say, involving F, so it relates to F1, and the other one is involving F2 in relation to G2. Suppose you have a nested loop. So you have like a for loop or a while loop, and then inside there you have another for loop and while loop. Now suppose that the number of operations that happen is F1 inside the innermost loop, and the outermost loop performs without consideration of what's happening in the innermost loop. So for example, say the innermost loop happens, say, n times, and say the outermost loop, the for loop, performs n iterations or something like that. Well, if you count up the number of operations that happen in the innermost loop, each one happens for each iteration of the outermost loop. Well, what does that count up to? It's a product like this. So if you figure out the big O for the innermost loop, and you figure out the big O for everything outside of that based on how many times it happens, like say, for example, you know, like the outermost loop, it's like a for loop that does n iterations, for example. Then it's saying that, okay, if you had big O many this operations, then you have big O many operations of the outermost part, then you can take the product of the 2. And it's really nice. So this is actually a nice general rule that you can use. Sometimes it's helpful when you want to quickly do a quick analysis. So just be clear what I mean by this. So say if you have a for loop and then another for loop, and there's some stuff that happens inside of here. And say this happens n times. And this happens, say, n times, just as an example. And say all the work that happens with this innermost part is, say, big O of n. And you know that this happens, this outermost for loop happens big O of n times. Well, because it's n, right? N is big O of n. Well, if I want to know how many operations happen in total over all of this, well, it's the product of these, because for each iteration of this, you do this, right? But I know how many operations happen in total is G1, and the other one, sorry, big O of G1 for the innermost part, and this is big O of G2 for the outermost part. So in this case, G1 and G2 are both n, and F1 and F2 are something like n. But yeah, so you can see that this manifests itself into some pretty hard and fast little rules that sometimes you learn in some introductory computer science classes, at least when you start talking about big O. But anyways, let's get into the proof, okay? So we're not going to worry so much about that. I just want to show you how you actually prove this. Remember, this is a statement about any two complexity functions. I'm just giving you an example over there of how this might manifest itself when you're doing time complexity analysis. So like when you analyze the running time of the algorithm. So anyways. So as per usual, we need to say what we're going to do, right? We need to give a game plan. So when somebody picks up your proof, they're like, what's happening? Somebody help! Help! They aren't doing that. In order to prove the claim, we find constants. So we find those two constants. Remember the two constants? So we usually call them C and N0. C and N0. Remember, C is a positive real number, N0 is a positive integer. And such that for all n greater equal to N0, we can say that F1 of n times F2 of n is less than or equal to C times G1 of n times G2 of n. The statement makes sense, everybody, right? So this is just us trying to prove this claim. But notice that I have this and have that at my disposal I can use in my proof, which is what we're going to use next. Cross my fingers, this one's better. So let's get in on this. If F1 is big O of G1 and F2 is big O of G2, then, like we've seen before, I can use their definitions, right? This means this. Remember, each one of those means I have pairs of constants, a C and an N0, but we got to give them different names so we don't confuse them with those ones. Just like if you think of like programming, you give different variable names for things that you already have names for those things. It reduces the ambiguity you might have when people are trying to understand what you're trying to say. Then by the definition of big O, because this is because of the definition of big O, we get the following. So let's head on over here. Come on over, okay? let's go over here. So we get the following. By the definition of big O, there exists constants. There exist constants C1 and C2, one for each application of the definition of big O. So I'm just going to call them C1 and C2. One for the first one involving F1 and G1. C2 for the one that involves F2 and G2. And And we have the other the other two constants, n1 and 2, which are going to correspond again to those two applications of the big O definition. So remember, we have two different ways we're applying the big O definition. For the sake of clarity, I'm just pairing them up like this so that you have the one for the first time and the one for the second one involving F1 and G1, the other one for F2 and G2. So let's get in on this, okay? So now I have that such that both, so we have these things that we could say as well, right? Such that both F1 of n is less than or equal to C1 times G1 of n. And this has to be true for all n greater or equal to n1 by the definition of big O, right? And we have that F2 of n is less than or equal to C2 times G2 of n for all n greater or equal to n2, right? So both of these are true. So already see that. So all I've done is I pulled out the definition of big O twice, and I'm just spilling out in a nice kind of uniform way each part of me using the definition of big O. So now I have those two things. I have these two inequalities. Akin to an example we've seen before, I'm going to try to pick it so that n is going to be at least n1 and n2, so that both of these are true. But here's the catch. Here's the catch. I want to make something that looks like F1 times F2 on the left-hand side. Well, does anybody see anything I can do here to make that happen? Well, before we usually just summed over the inequalities, can I like multiply? Like, sure, I can multiply. Let's try multiplying, okay? So watch this. Then I'm going to pick n0 up front, just because I feel like it adds a little bit of spice to the discussion here. By selecting n0 is equal to the max. So remember, max just simply means I take the larger of the two values. So I take the larger of n1, n2. And I observe by multiplying, so we'll say multiplying over, we're taking the product over, multiplying over the two above inequalities, these two above inequalities, for all n greater or equal to n0, because I made n0 big enough, so I could just use these two facts. I have these two now because n0 is big enough. Then I'm going to just f1 of n times f2 of n. Well, if I take the product of these, then I have to take the product of both sides, right? So I have f1 times f2, and I have c1 times g1 times c2 times g2, all on the right-hand side. So I have the first term, c1 times g1, and this is multiplied by c2 times g2. But if you rearrange this, akin to one of our other examples, you're going to see that I can take c1 times c2, because remember, I have c1 times g1 times c2 times g2. I can always permute products like this, because they're just numbers at the end of the day. When I look at the outputs of these, the order here does not matter. I can just commute or permute, if you would like to call them that. I can take these two. I'm just going to pull them out front like this. Then I have g1 times g2. But look at this. Look at this. Now I have c1 times c2 times this thing. This is what I wanted, right? f1 times f2 is less than or equal to some constant times g1 times g2, right? But what's this? Well, if I make this c, we're done, right? So choose, well, let me put a period at the end of this. So choose c is equal to c1 times c2. Therefore, by the definition of big O, we can say that f1 times F2 is in fact big O of G1 times G2 all together in there in the big O. And we're done. End of proof. Piece of cake, right? So you'll notice I'm just using the same types of bucketing strategies. And that's really it. That's really it.